Via de lead given.
So let's start again on waveguide is the topic of the week. So yesterday we really entered in with theory of waveguide formation. Dielectric waveguide, which means also semiconductor waveguide in case of indium phosphate or silicon, but semiconductor used without injecting carrier, so you can see as a dielectric. We will use this kind of material in a more, let's say, advanced way. The modulators, so the detectors, the whole laser, but this will be at the end of the course. So today, once again, waveguide. I want to finish the chapter waveguide and also band waveguide. Next week, I'm not here, but there is a postdoc that substitutes me, 3 lessons, and we'll have a lesson on the simulation of waveguide. So basically, the concept of mode, the propagation, the band, etc. But with example, with a numerical example, and you see the simulation, you see the movie, you see the shape of the mode, and it's a good occasion to ask, if you want to see something, just ask, and he can simulate real time, so it's good. Right. And then probably I started today, but you will finish the problem. You will finish. No, we'll touch the problematic of couple the light from an optical fiber or a laser or something that is external to the chip to the waveguide. So the coupling is not so easy. It will touch something, and we will focus on this when we do silicon photonics at the end of the course. And the other topic that he will do is technologies. So how to build, how to realize waveguide and so photonic circuit on chip. So we'll be back next the week after, so we can continue with our course. So yesterday we really entered in the theory of electromagnetic theory of wave guiding. I don't know if it was an heavy lesson or if you digest the topic, you have problem, you have question, you have curiosity, everything is clear or everything is unclear. More or less clear. Good. I say once again, it's very important that you understand the phenomenology, the physics behind, and the parameter, geometrical and physical parameter that play in the topic that you are considering. Try to remember the most simple and important formula, not everyone, because there are a lot. A formula can be found on the book. It's important that you understand where find the formula that you need. So use your neuron. You have still a few neurons free at your age. Already done. And use your neuron to understand really the link between the physical and geometrical parameter and the transfer function, the function, the functionality of the device, the link between these two. So you have to know what's happened if you shrink the waveguide, what's happening if you change the wavelength, what's happening if you do something. So try to make a clear picture in your mind about what we study. The formula are clearly important, but just the most important, the most simple. Okay? The message is clear, and I will say again. Right. So, probably it's better that I summarize the lesson of yesterday very quickly and touching the most important part, so you understand which are the most important part from my point of view. And in case of question, just stop me. Okay. So, electromagnetic approach. So I pass my note and I stop where I see something that I think it's better to say again. We consider the slab waveguide, no? So it's an infinite plane of dielectric of core. Why is it important? Why we start from this one? First of all, because it is, from an educational point of view, easier to work with. It's just one variable, 1D, is not a 2D, so it's easier to work with. And we can arrive to some closed form formula, or at least an analytical approach to the problem. If we started with a square or rectangular waveguide, it's really difficult, it's impossible. So, and there are devices that use, let's say, a very broad waveguide. So it's like a slab. It's like a slab. At some point you have to finish because of the finite dimension of the chip. But you can think as a plane waveguide. So as a slab. So it's not just an academic exercise, but it's something useful. Another point, the thickness of the slab is H. NW is the refractive index of the slab. Let's see, NS. Let's consider a symmetric waveguide, and assume you have NS equal to 144 and W 145. this is a 0.7% index contrast, so it's very low index contrast. And we wanted to design this waveguide. So the thickness, in order to have, this is H, I, and N, not mixed with N. The cutoff frequency of the second order mode is given by this formula. Lambda C means cutoff, 2 square root of the refractive index of the waveguide minus the refractive index of the surrounding material to the square. This is the cutoff frequency of the second mode. So we know that the mode has a shape like this. This is the first one that is usually called the T0. TE means transverse electric mode. 0 because it's the fundamental one. And the second one is something like this. TE1. So we are interested to work with this guy. Okay. We don't want this one. So we calculate the cutoff frequency of the T1 and we stay away from the frequency. The cutoff frequency of this one is less. How much less? How much is the cutoff wavelength of this T0 model? 2.4 what?
Ah,
2.4 what? Meters? Liters? Hertz? Is a symmetric waveguide, is a symmetric slab waveguide, so the fundamental mode does not have the cutoff. So the wavelength, the cutoff wavelength is infinite. The cutoff frequency is 0. Then we can discuss if a very low frequency is guided well, is guided efficiently by this waveguide or not. But this is another point of view. So the cutoff frequency of this mode is infinite. So we are interested to know this one. Let's reverse the problem. We want to work at 155 micrometers, so 1550 nanometer is the classical wavelength, the classical frequency. Giorno? The classical frequency of optical communication today. So if we put the 155 here, we find a thickness of 456 micrometer. So we have a slab with a refractive index of 145. The surrounding material is 144. Okay. If the thickness is 4.56 micrometer, this mode is guided, and this mode is at the cutoff. So if we do 1.55, a little bit thinner, the T propagated T0 and the T1 is radiative. If we increase a little bit, we propagate both modes. At 156, just at the border, so it's difficult to say what's happening. You can reverse and say at 456 micron, the wavelength 1.56, so longer wavelength, lower frequency, you have the T0 and you don't have the T1 because the T1 is then the cutoff. At a shorter wavelength, T0 and T1 are both solution of the wave equation, so both can propagate. Okay? So this is the way of thinking that I would like to pass you. Which formula do you have to remember? Well, it's a very simple one. You are used to remember very complicated formula. So just need this one. But obviously, you have to be, well, obviously, from my point of view, you must be able to do this kind of thinking, you know? What's happening if you shrink a little bit? What's happening if you enlarge? What's happening if this is not 4 or 5, but 4, 6? This mode is in the cutoff, the other one no. We are far away from the cutoff. What's happening if we are far away or close to the cutoff, etc. So the physics behind and the right. Questions? Assume that now ns is equal to 1 and n of the waveguide is a silicon, so the refractive index is much higher. This is glass, this is silicon as material. A slab of silicon suspended in the air. People know how to do it. It's not difficult. The other one is doped glass in glass. So if you do again the calculation, the thickness of the waveguide is 0.23 microns, so 230 nanometer. But not many atoms. The dimension of the atom of silicon, the distance between two atoms is half a nanometer, so it's less than 500 atoms. So this is nanotechnology. This is really nanotechnology. So you see a much smaller waveguide. We change the refractive index. The index contrast is much stronger. The light is much more confined. And if you want to work in the single mode regime, you need a much thinner waveguide. This has a tremendous impact on the technology, because if you wanted to build this waveguide or this waveguide, well, the technology is not the same. Here you have to control really the nanometer. This one is much larger. Okay. Try to play with this number and try to see, for example, a silicon waveguide embedded in silica. So this is 1.45. How much is the thickness? Try to see where the third mode started to propagate. Remember that here there is an n in the formula. So we have 0, but 0 does not make sense because it's a symmetric waveguide, or 1 in case of T1. If you wanted the third order mode, or the second order mode, then this is equal to 2. So you divide basically by 2 these dimensions, and so on. Okay, so very, very simple consideration, but very important for my point of view. If you have questions, if you don't understand something, just stop me and
Can you repeat, how did you find the number of atoms of the distance thickness? You said
the distance between 2 atoms in crystalline silicon is more or less half a nanometer. Okay. Let me see if there is something else from yesterday to repeat or to put the accent on. The omega beta diagram is clear.
Sorry, dispersion diagram. Omega isn't dispersion diagram.
The dispersion diagram, yes, this is another name of the omega beta diagram, yes, right. You understand now that beta is very important for us. Beta is it's called the eigenvalue, is the solution of the wave equation, and is a wave vector because the light propagates is an exponential plus minus in case go back. So it's a wave vector, so wave vector is 2 pi divided by lambda multiplied by the refractive index. This is not really a physical refractive index because the mode is spread around the core, so it's an average refractive index, but we like to write 2 pi divided by lambda, and so we add this term that we call effective index that is particularly important. So the omega beta diagram, or dispersion diagram, is something like this. If you define a frequency, you get the solution of the wave equation. So the eigenvalue, so the phase constant of the mode, and the eigenvector, so the shape of the mode. So for this reason, it's very important. So now the ratio between omega and beta is the slope of this segment. So the slope of this segment, omega over beta, is the phase velocity. So the speed of the light in the vacuum divided by the effective index. If you substitute the expression of beta and omega in this relation. No? So this slope is the phase velocity. This slope is the phase velocity of the light in the substrate, and this is the phase velocity of the light in the core material. The core material. So your solution stays between these two lines, and the slope of this segment is c divided by the effective index, so the speed of the light of the mode. And obviously, as the mode does not change the shape during the propagation, every point of the mode propagates with the same speed, with the same beta. Obviously. even if the materials are different. Okay?
Again, this is beta is constant in the box.
Absolutely, yes. This is the way we impose the continuity equation, the continuity of the field across the interface. So beta is the same. The field outside behaves as this, the field outside inside again by this. So you have the continuity of these two. These two must be equal in every point, in every zeta. So this is the only way to achieve the continuity of the field everywhere.
There is a point I didn't understand. When the fundamental mode is infinity, we don't have propagation. The fundamental mode, no. Yes.
As a cutoff that
Yes,
is
cutoff.
very low frequency, even zero, theoretically zero. And yesterday I showed you the shape of the mode by changing the wavelength, changing the frequency, and change a little bit the shape, because change beta, change the shape, etc. So if you decrease the frequency, so increase the wavelength, you have a more broad mode, and if you decrease, you get really something, it is huge compared to the chord. In practice, is no more guided, but from a theoretical point of view, is guided. Exists the solution. The solution exists. So go back to this point. This is the phase velocity. We introduced the group velocity yesterday. The group velocity is nice to define as the speed of the light divided by refractive index. This is the group velocity, and we call group index the relative refractive index. And is the velocity. So once again, is a slope on this diagram, and is the slope of the tangent here. So this is the group velocity. And so this is the derivative of omega with respect to beta. And yesterday I gave you the expression of when I started yesterday, I said I started with saying that the three component of the there was two components of the electric field, and one of the magnetic field was zero. The other solution is called TM, and there is a mode very similar to this one, but is transverse magnetic, so does not have a field in the direction of propagation. So you always have T and TM. So everything we say is valid for T and TM, that we have an effective index for the T and an effective index for the TM. We have a group index for the T and a group index for the TM. We have an attenuation for the T and for the TM, etc. So everything is double. The cutoff frequency of the two solutions are very similar, and the behavior are similar or not depend on the technology and on the shape of the waveguide and the refractive index. If you have a square waveguide, for example, a square waveguide, the T and TM have the same behavior. You can have effective index of the T equal to the effective index of the Tm. So this is the and the waveguide is a symmetric. So NW and SR. So perfectly square waveguide, symmetric. The T and Tm behave the same way, and so the two effective index are exactly the same. But you can think of waveguide very asymmetric. So, for example, you have a substrate of silica, a thin layer of silicon and air on top. This is silicon. So 3.45. This is a classical waveguide. Rectangular with a very strong aspect ratio. So basically a strip of the electric. Well, in this case, the effective index of the T is much larger than the effective index of the Tm. But you can even reach a condition in which the Tm mode is not at the cutoff, but is very weakly guided, is badly guided. So you see, different waveguides have a very different behavior. In general, we always have T and Tm solution. So T and Tm mode. In some waveguides are very similar, in other waveguides are very different. So what we want in general? We want similar behavior or not? Well, if you think to the application to optical communication, you arrive with a fiber, you enter in your chip, in your device, and you want to do some processing, you basically don't know the polarization. The T mode basically has a field, electric field in this direction, while the Tm mode has an electric field in this direction. So, if you arrive with an optical fiber that is a cylinder and you don't control the polarization, you don't know the polarization of the light that arrives on your waveguide. So you can excite the T, you can excite the Tn, or you can excite both. In general, you excite both because you arrive with a strange polarization. So you excite both solution, both modes. So if the behavior of your device, whatever it is, depends on the characteristic of the mode, so on the effective index, on the group index, on the attenuation, etc., it is clear that the transfer function of your device depends on the polarization of the light, depends on the mode. So assume you have a filter centered a given wavelength because you want to filter out a channel or whatever. The position of the filter depends on the effective index. So if you enter with a T or the Tm, you have a different filter. So for this kind of application, it's very important to have the effective index of the T equal to the effective index of the Tm. So the behavior of your device is independent of the polarization. So we are talking about a polarization independent device.
Are you saying when light passes an optical fiber, we don't know the polarization?
You cannot really control the polarization because you launch your polarization at the beginning and this one tends to rotate, to change, depends on the bend, the twist, the stress, the temperature, or whatever.
So how do we make both the same? for having similar filter characteristics, how do we make the N effective for TE and TMC?
This is a good question, but there is no answer at the moment. People is working hard on this. It's not easy. And yeah, it's a problem. There are two techniques to obtain polarization independent device. We will see during the course. One possibility is to really work on the technology of the waveguide and achieve this equality. So having two effective index identical. Identical, from an engineering point of view, means that is the first digit are similar, but at some point are different. No? So you always have a difference between these two. 10 to minus 4, 10 to minus 5, 10 to minus 6, I don't know, but so identical with which accuracy, first of all. Okay, assume you can control the technology and achieve this condition, then your device is polarization independent. This is very difficult to achieve and very expensive from the technology point of view. The other possibility, I didn't want to talk about this, but as you make the question, the other possibility is just a very simple explanation. Then we probably go back to this point. At the end of the optical fiber, you split the polarization in two. So you center the vertical polarization on one side and the horizontal polarization on the other side. Okay, so you have the T and the TM mode. Then you put two physical devices, one that works only on the T, designed in order to work properly with the T, and another one designed to work properly with the TM. So you can do, in case of a filter, the same transfer function, and then you combine the two polarization again. So you have to split the polarization to double everything. It's very heavy, very difficult, very expensive solution. People don't like it, but this can be the solution of the problem.
Professor, what about TEM modes? I mean, we are always talking about TE and TM modes, but what about TEM modes?
TEM does not exist.
In optical
No,
systems?
in guided wave. Guided wave. You don't have a solution in guided wave. Electrical or optical does not make difference. No, it's just electromagnetic field. Electromagnetic field does not exist a solution for which both E and H field, electric magnetic field in the direction of propagation is equal to 0. This is the condition to have a TEM mode. Good point, thank you. And this is the solution for a plane wave in free space. Sometimes in some guiding structure you can arrive very close to this condition, so maybe you can say this is a TEM mode, but rigorously is not TEM. And in dielectric waveguide you never reach this condition. Good. Thank you for the question. I like this interaction because don't be worried to do stupid question. So the question is a question.
The polarization
Be
can
careful.
be adjusted by the mean of these using digital, the polarization can be adjusted using DSP.
Using
DSP, digital signal processing.
digital signal processing.
We started in.
We took this in optical fiber. We took the same, we split the balls, and we took this in an differential amplifier, or by using of DSP. It was just a general idea about.
Sorry, it's difficult to avoid to give not well. I'm electromagnetic. I'm from electromagnetic field, so my answer can be different from people from system. Okay, you have already understood this point. Try to understand to reply correctly. The polarization in the optical fiber is not controlled because of the shape of the geometry of the fiber itself. So it's not conserved. Go out. Okay. If you at some point of the link use photonic device, this must be polarization independent, because otherwise, no, the behavior of the device depends on the polarization. It's something that you don't want. So, either you control the polarization when arrive and you put the polarization or your field in the right position, or you use polarization independent device. You have these two options. There are no other options. No? Okay. So assuming you wanted to use polarization independent device, how to do it? One possibility is this one, quite demanding from a technology point of view. Okay. So as we started this discussion, now I'll give you some number. The other possibility is the one that I mentioned before. So split the two polarization and treat the two polarization together. Then what you want to do? You want to do a receiver. Well, this is a possible device. It's not, no, it's one device. So if your aim, your scope is to make a receiver, so to move the information from the optical domain to the electrical domain, well, at some point you need this digital signal processing in order to process everything, but not only for the polarization, for the inter-symbol interference, for distortion, for everything, you know. And this is a discussion that is ongoing. It's very interesting in this year. So it is clear that you can do everything, signal processing in the optical domain or in the electrical domain. If you want to do the signal processing in the optical domain, in the electrical domain, you have to access to the phase. And the only way to access to the phase is to do a coherent detection. So you see, we are talking about a very specific device, a receiver. Okay, this is one of our devices, but it's not the only one. I'm interested in other device, totally transparent device, where you can treat the optic. In any case, you can do everything optically, or you can do everything electrically, or something in between. You do some signal processing in optics, then you move to electric, and you continue electric. And the border is not clear. Where is the best place? How much do in optics, how much do in electrical? And this is the ongoing discussion in our journal, our conference, our meeting. There are European projects dedicate millions of euros dedicated to this point. So, no, something difficult to reply in just a few minutes. As every other question, you never succeed to say which solution is better. It depends on technology. Okay, so but it's clear that the polarization management is something that is not easy at all. I say I give you some number as an example. This waveguide, 230 nanometer thick. Okay. If you change this dimension by 1 nanometer, is a lot or not? I would say no. It's just a negligible shrinking of. It's just 2 atoms. It's the width of the waveguide. You remove 1 atom on one side, so it's just a little bit. Okay. In this waveguide that I show you, this means a shift of the transfer function by 1 nanometer. That means 125 gigahertz. Is more than the channel spacing WDM system. So you want to build, you are not able, but you want to build a filter at 1 wavelength, you design, you build, and if you make this error with technology to shrink the waveguide by 2 atoms, your filter appears 125 gigahertz away from the position you designed. Okay? This is the sensitivity of integrated optics today and tomorrow, because the material is in silicon. This waveguide is much less sensitive. But it's much bigger, much larger. So a little bit lost from all this discussion. Any other question? I can continue. Or... Yes. All this story started because I wanted to introduce the birefringes. So the difference between the effective index of the T and TM is important, and people gave a name, and the name is birefringes. And it's the difference between the effective index of the 2 modes, T and TM. It's called B birefringes of the waveguide.
Excuse me, can you please write how it is written?
Yes.
Can you explain again the sensitivity of the integrated optics?
The
integrated optics sensitivity that you explained now. When we change the edge.
The sensitivity to the width.
Yes, when it was 230 nanometer, what was the wavelength? It was one.
Reference wavelength. 1550. I don't know the number. You design your filter at 1 wavelength, say a number.
1.5.
1.5, okay. Then you shrink the waveguide by 1 nanometer, and your filter is no more at 1.5, but at 1.501. I wanted to do another example. We are talking about mode. I want to. Okay. Assume we have a waveguide. This is the 0. We start from here. The waveguide is very thick, as you can see, and 2 modes can be guided. In the previous example, think to this waveguide with a thicker wavelength, thicker high with respect to the number we calculated before. So 2 modes can be propagated. Okay? So the 2 modes are the fundamental mode T0, that is something like this, T is 0, and the other one is the T1, that is something like this. T1. Okay. These are 2 modes of the structure, so are orthogonal in space and in time. They don't talk each other, they do not exchange power, they propagate at a different speed. So this one propagates as beta 0, zeta, and this one propagates as very similar expression, identical expression, but a different value. Because this is the nef 0 and this is the nef 1. Okay? So these 2 modes propagate. Assume they have a very similar amplitude, the same amplitude. They start in 0. So in 0, they have the same amplitude and assume the same phase. So can be drawn like my drawing, as I did. In another point, the T0 mode accumulated the phase that is equal to beta 0 multiplied by the zeta star, where zeta star is this position. The second mode, so this is Phi0, the second mode, the amplitude is the same because there is no losses, is a guided mode, so the amplitude does not change. But the phase of this mode, T1, is beta 1 zeta star. So it's different, no? With respect to the previous one, because they travel at a different speed. So if at some point, assume this one, at some point here, for example, in this position, delta phi, so phi1, phi0 minus phi1 is equal to half pi, it means that your mode are now just a second. Sorry, pi, let's say pi. If the distance is pi, it means that if we draw the first mode like this, and we take as reference, the other one has this shape, because the shape does not change, this amplitude, because the amplitude does not change, but the opposite phase. So you have to draw this field, because they are out of phase. So in this position, we have delta beta multiplied by zeta equal to pi. And if we continue to propagate, at some point where delta beta zeta is 2 pi, they are back in phase. Okay? So why I'm telling you this story? First of all, because it's another exercise on mode. To enforce the fact that the mode does not change, the amplitude does not change the phase, the modes are orthogonal, they do not exchange power, they don't talk each other, they travel at different speed, blah blah blah, what we said yesterday. Okay. And three reasons. The second reason is this is a two-mode waveguide, but if I draw this, these are the solution. Then you can put the power on this one, or both. So you can excite, you know, if you put here a fiber or a laser or something else, you shine the light on the waveguide, you can excite one, the other one, or both, depending on the shape of the field that arrives. So if this is really a highway with the two lane, and you put the car on one side, on the other one, or both. The lane are the mode, are the solution. The car are the power on the modes. Okay? Good. And the third reason is to introduce the next topic that probably is not next week, but the week after, but it's better to try to draw the total field. Total field. Assuming you have an instrument, you want to measure the intensity of the total field. So you have to add the two. So the total field here is something that goes up here, these two parts cancel. So it's something like this. Oops. Terrible. Do it again. Sorry. This is here and this is 0. So it's something like this. Here is the opposite. So it's 0 here, pass from here, and then go down. So here is a field that is like this. So you see, if you look at the total field, it seems that it moves down and then moves up again. So you have a sort of bouncing of the field around the inside of the core. the mode does not exchange power, the mode does not change shape, they continue to travel, but the total field somewhere is in the upper part, somewhere in the lower part, somewhere is in the middle. So keep well separated the total intensity of the field inside the waveguide and the excitation of mode, the intensity of the mode. And this fact that the field change shape is due to the interaction of the mode, of different speed, different and this really introduces the coupled mode theory and the directional coupler that are the first device, the first building block that we will see. It was good to introduce now because we are talking about waveguide, modes, and so on. Questions?
2 minutes ago, before you said that modes do not interact with each other. And now you said that you change the shape because modes interact.
The field changed the shape, not the mode. The total field.
But do they interact or not?
No. No. They do not interact.
You say you change the shape.
The total field.
Total field changes.
This is what we call the fizzy, I usually the same. This is the
Total. I got it.
this one and this one are the mode, and this is the total field. So this is the combination of the two. You remember the expression of the total field is a combination of the modes.
We always operate in the normal mode, right?
90% of the time, yes.
How the field is working in the normal mode? It's more stable, not bouncing like this.
There are no this kind of effect.
Yes.
Unless you wanted to induce this effect. And then in the directional coupler, we will see the directional coupler, we exploit this effect. We want this.
But we overcome this, or we want it to be bouncing. We overcome this unstable propagation.
No, we exploit, we induce this, I don't call it unstable. Unstable is not a correct word. We induce this one and we exploit. In 2 weeks you will know.
So the bounce of the field is useful to us. The bounce of the field is useful.
Is useful. So sometimes it's useful, sometimes it's not useful. So it's good to know. Because if you know, you can exploit and you can avoid. I think that this is a good summary of what we have done yesterday. And with some integration, with main integration. So now we do a black and then we continue with 2D waveguide. So the right waveguide